All right, in this video, I'm going to introduce you to the chain rule for multivariable functions. You should know the chain rule from 2D calculus, derivative of the inside times the derivative outside with the old inside, right? This is related and it's similar, and fundamentally it's the same thing, but there's lots of different formulas. I'm also only going to go through the basic, simple version because that's all I really care about right now. All right, so say I have z equals f of x comma y, which is a multivariable function. And then x is actually a function of time, and same with y. Then I have a special way to write the derivative of this thing. So what I can write is the derivative with respect to time of f of x of t, comma y of t. So the inputs for f are actually these functions of time. I'm going to write it in, I think, 3 different ways. That is f sub x times dx dt plus f sub y times dy dt. So that's one way to write it. The other way to write it, notice this is, well, I'll write it with partial notation. So it is partial f partial x times dx dt. You may say, oh yeah, sweet, this and that cancel, but they don't, okay? So this d and that partial sign don't cancel. Plus partial f partial y times dy dt. I'm not going to go into too much why they don't cancel, but if they did cancel, then like the partial y and the dy would cancel. I would get partial f dt and partial f dt, and when I have 2 of them, no, it's just these are just what they are, and you'll see as I move along. Okay. The other way to write this in a more simple way is actually with the dot product. Notice I really have f sub x comma f sub y dotted with the vector x prime of t comma y prime of t. I kind of prefer this and that. I like those 2 notations for this thing. This because it's more useful when I'm trying to do things with it, and this just because it's easier to read than this mess here. So let me show you what this means. I'm going to do it with an example. Let's take the example x of t equal to t squared and y of t equal to sine t, and f of x comma y equal to x cubed y plus cosine x. So the first thing that I'm going to do here is try to convince you that this mess is actually something for which I can take the derivative with respect to time. Because when you look at this at first, you're like, what? Like there's the f sub x, right? It just doesn't intuitively make sense. But watch. What I can do is, this is method 1. And this is not using the chain rule, okay? Well, the chain rule that I just wrote there. It's kind of reducing it down. So what I'm going to do is f of t equals, what I'm going to do here, look, I got f of x comma y. And here x is a function of t and y is a function of t. So what I'm going to do is plug in x and y as functions of t. What do I mean by that? Well, look, I got x cubed here. So cubed, and then what am I going to put in there? This t squared right here. And then I got a y, so it's y. Y is sine t. And then I got cosine of x, so it's plus cosine of, and what's x? That's t squared. So when I simplify, I get t to the 6 sine t plus cosine of t squared. So what I want you to recognize here is that if x is a function of t and y is a function of t, and f is a function of x and y, then f is actually really just fundamentally a function of time. Okay, as you can see right there, which means I can take the derivative with respect to time. So let's do that. Dt of f of t is equal to, well, this is just like basic calculus. Product rule, 6t to the 5th sine t plus t to the 6th cosine t. That's the product. And then plus, this is like, regular chain rule from 2D calculus. I get a, oh, whoops, not a plus. I get a minus 2t cosine, or sorry, sine of t squared. So you may say, all right, cool. I can do this, right? I can find ddt of f of t. I can find the derivative here. Why do I need the chain rule? Well, there are times where we can't do what we just did. So I need to take this chain rule here. So let me copy this and put it down here. Actually, maybe I'll make it small over there as like a side piece. And I'm going to calculate this same thing, but using the chain rule. So let's rewrite some things. So this is method 2. With chain. So the more complex chain up there. So let's look. F of x comma y is equal to x cubed y plus cosine x. All right, let's find del f. That's equal to 3x squared y minus, or sorry, yeah, that's 3x squared y minus sine x. That's the partial x. And then the partial y is actually really simple because there's only a y here. So I get x cubed. Okay, this is f sub x. This, oops, not that. This is f sub y. So now, remember, x of t was t squared, and y of t was equal to, what did I use? Sine t. So that means that x prime of t is equal to 2t, and y prime of t, so these are derivatives with respect to time, is equal to cosine t. So let's use this formula right here. So f sub x is, so let's do dt of f of x of t comma y of t. Do I need another parenthesis in there? I do. Okay. All right. That is equal to, all right, f sub x. What's that? All right, it's this thing. 3x squared y minus sine x times, all right, what's dx dt? It's 2t. Plus, what do we got here? F sub y is x cubed. That's this, times cosine t. And now you may be like, well, that's not this, right? But it is. Why is that? Because now what I can do is I can plug in my t squared for x and x and x, and I can plug in my sine t for y, and is there another y? No, that's it, right? So I'm going to plug those guys in and watch. It's going to give me the same thing that I have up top. So it is 3 times x is t squared. It's got to be squared again, times sine t minus sine of, what do we got, t squared, all that times 2t, plus, all right, what do we got here? X cubed, x is t squared cubed, times cosine t. Now notice everything's got t's in it. This is a squared here. A little better now. But so let me go through. So this is, all right, I'm going to distribute this 2t in. I got 3 times t squared squared. That's t to the 4th. So I got 3t to the 4th times 2t. That is 6t to the 5th. All right, that gets multiplied by sine t. And then minus, all right, 2t gets multiplied by here, 2t, sine of t squared. And then plus, what do I get here? T to the 6 cosine t. Now look, this is the same as what we have up here. So, look, they got all the same pieces. It's just this one's flip-flopped with that one. So, it may be, you may say what I said earlier, which is like, well, why don't I just do this, right? Well, sometimes we cannot do just that. In addition, this is kind of the more simple version, of the chain rule. For example, I could have a 3D input equation, f of x, comma y, comma z, but each x and y and z could be dependent on 2 other variables. So if I were to do that, it'd be something like f of x of s, comma t. Those are my 2 inputs instead of just a single t, comma y of s, comma t, comma z of s, comma t. And doing that chain rule is sort of more complicated than this up here, but it follows the same ideas. But at this point, I don't care about using that other chain rule, so we're not going to talk about it. I only care about being able to say, if I've got something like this, I can write it like this, right? So hopefully you are convinced that this right here is true if I've got f of x of y, and x and y are both dependent on a single variable t. And if you see that, then we're good to go, and we can take this next step that we need to take.